Hello everybody. So we are going for the review of the key concepts uh, of the last 3 weeks what we have studied in your regular course. So this will be the last review for the key concepts on theory and applications in thermal and cold plasma. So in this, the concepts that we have covered includes atomic and ionic emission lines, molecular bands, species identification, plasma particle interactions, tools for temperature, velocity and density distributions of particles in plasma jet, Langmuir probe principles, limitations. Then we have covered the plasma technology areas for renewable energy and environment, plasma pyrolysis, gasification, incineration, waste to energy concepts, and societal applications. Then some industrial applications like plasma cutting, welding. Then we went for plasma in medicine, cold plasma application for cancer therapy, synthesis of nanocomposites, functionalization, and targeted drug delivery. Then we have covered plasma in agriculture, synthesis of nitrate fertilizer, seed germination, plasma catalysis. Then plasma in synthesis of novel materials like nanosynthesis, top down and bottom up approaches, homogeneous nucleation. Then unimodal and bimodal size distribution, size control principles, and plasma coating. So, we start with the image analysis techniques for easy mapping of plasma temperature inside an external plasma jet. So, this is basically a very rough idea about the distribution of temperature inside a plasma jet. So, this just gives you an approximate idea about the distribution of temperature inside a plasma jet. In this figure, what we are seeing a nitrogen plasma jet in this figure A, then experimentally measured band spectra at location, this location what we are showing by this P, this one. So this is the spectra that we have got, and from the structure itself you can see that this is a band spectra. And then this one is the simulated spectra. So you can simulate this band spectra at different temperatures, and what we are seeing that at 7700 degree Kelvin the spectra which has been simulated matching very well with the experimental spectra. So we then conclude that roughly the temperature of this location here, this location actually the plasma jet, is 7700 degree Kelvin. Then taking just the image, we go for iso intensity contours within the plasma using jet scalar scheme of MATLAB. And what you are seeing, this is the iso intensity contours, and this location is the location where from we have determined that the temperature is 7700 degree Kelvin comparing simulated and experimental spectra. So wherever you find the same intensity from this iso intensity contours, you can say that the temperature is 7700 along this contour. Okay, whatever this red the thing is there. So this red one is the the 7700 degree Kelvin, which is the maximum one that is over here, and that we have measured as the 7700. So remaining contours you can see that if we go for this color scheme, then you can get the temperatures accordingly. But I should tell you that this is not a very accurate estimation, only you get some rough idea, because wherever the similar intensities you will get, you can expect that they will be having the similar temperatures. Now coming to the line emission spectra that we have seen in many of the slides in our regular classes, they are actually not lines. They do have some broadened profile. So here from the broadening comes, we have discussed different broadening mechanisms like Doppler broadening, intrinsic broadening, Van der Waals broadening, instrumental broadening, resonance broadening, and then Stark broadening. Because in plasma there are charged particles, and naturally they are exposed to intense electric field due to the discharge configuration itself. So the broadening of the line occurs through Stark broadening as a major broadening mechanism compared to the others what is listed over here. So once you do that, you see that here we have got a line spectra emission that we have recorded using spectrometer, and this is the H alpha line. It is a famous line of this hydrogen atom, and you are seeing here that this is the line, wavelength of that line 656.28 nanometer. But what you are seeing here that it is having a broadened profile. But you have probably noticed that 656 is not matching with here, because it is center is somewhere around more than 657. So that is happening because that there is a shift in the instrument which is recording. So you have to adjust the shift so that you get the exact 656.28 nanometer at the center location here. Okay. Now what is important is the broadening here, and what we are seeing that the half width at full maxima, this is 0.33 nanometer. So we have made a Lorentzian fit. Now you know that for a given plasma, if we know the temperature, then we can estimate different broadening contribution like Doppler broadening contribution like this, Van der Waals broadening contribution like this, and resonance broadening gives like this. Most of the parameters which are there in this equation, they are available in literature, so we can estimate these values. So finally the Stokes broadening contribution we get by subtracting the contribution from the others like this. So this is what the broadening you are getting, and from that you are subtracting the instrumental broadening, Van der Waals broadening, which are the major contributions here, and you can subtract other broadening contributions if they are significant. Then what you get, the true contribution from the Stokes, not this on Stokes, it will be Stark broadening. So this is written wrong. So it will be Stark's broadening. Now this delta lambda S, that comes to be like this. So this is the Stark broadening which happens because of the electric field inside the plasma, and that comes to be like this and related to the electron density as Ne to the power 2 by 3 with these factors. So if you know the broadening, if you come to know the broadening from the experiment, then you get the idea about the electron number density within the plasma. So this is a very interesting method to determine the number density inside the plasma. Then regarding the temperature, we have used the Boltzmann plot technique by which we can determine the temperature. We have discussed that very elaborately in our regular classes. Now comes the Langmuir probe measurement. This type of measurement are invasive measurement, while the previous one what you are seeing here, they are remote measurement, non-invasive measurement, because you are just recording the emission spectra from the plasma. So you can apply this to thermal plasma where the gas temperature is very high. Similarly, Boltzmann plot technique, it is applicable to your this thermal plasma as well. Now coming to the cold plasma where your gas temperature is very low, so melting of the probes is not a concern here. You can very well determine the number density and the temperature of the plasma using the Langmuir probe. So here what you basically address the electron temperature, and because the gas temperature is very low, you can measure that by number of methods, including the normal mercury thermometer or using your thermocouples. So you can get those gas temperature measurement done, but this Langmuir probe measurement is specifically for electron temperature and electron number density. As you are seeing here, we have used number of types of probes like spherical, cylindrical, planar tips. Now, for each of them, the characteristic of the voltage current relationship, that is a bit different because of the shape, but anyway from each of them you can extract the number density and the electron temperature. So typical probes, their diameters and probe lengths we have already discussed. For laboratory plasma, fusion devices, space plasma and RF plasma, as we are seeing that they are probe tip diameter all in the range of millimeters, say from fraction of a millimeter to several millimeters, that is all. And as far as length is concerned, only in space plasma you are seeing that it is of the order of several centimeter, but otherwise it is say a few millimeter to say few centimeter only the probe length, and you see the probe diameter, it is of the order of millimeter. And the material which has been used there, many material have been tied, tungsten, molybdenum, graphite, platinum, stainless steels. Each of them has some pros and some cons. I have listed it over there. So what basically you require, the material should have high electrical conductivity, high melting point, chemical and thermal stability and mechanical durability. So these are the characteristics that you require for the Langmuir probe material. Now the typical connection that you do for Langmuir probe measurement, so this is the discharge tube, is the plasma, and these are the electrons. You see that we have biased the probe, this red one is the probe, using some power supply. So depending on the kind of bias, the electrons either will be repelled or it will be attracted, and when you sweep the voltage from high negative to high positive value, you get a VI characteristic that gives you the information about the plasma temperature and the electron density. So these are the basic idea. Insert a small metal electrode in the form of wire, spherule or plain plate inside the plasma, make a complete circuit and bias the electrode. Probe current can be determined using oscilloscope. Plasma parameters can be determined by loading the probe with various voltages. Usually we give a RAM which runs from high negative to high positive value, and what we get a characteristic of this type. When the probe bias is negative, only ions are getting collected, and this is the ion saturation current. And then as you increase the bias, then this linear region you get, and then when the probe bias is positive, then they are able to collect all the most of the electrons, and the this current saturates. But this region is bit different for planar electrode, cylindrical electrode and spherical electrode, as you are seeing. But anyway, you do have a point Ni. So that gives you the Ni potential, that is pi 0, and this is the floating potential of the plasma. So once you get this curve, then this you note the ion saturation current. you know, in the linear region, when you are applying a very large potential, then you are getting the current J, which is almost constant over there, as you have seen there for your planar electrode, and then for moderate positive potential you get the linear region. So that is of interest, and you get a relationship of this kind when you plot this log of Jp plus Ji as a function of phi by applied potential. Then log when you take, then this becomes a linear curve, and what you get the slope as E by KTE. So if we are able to measure the slope, you know the temperature TE. Like this, you just alter the parameters and you get T is equal to E by Gk, where G is the slope of that curve. And then what you get, the electron number density, comes from the flux. So this current density, what you are getting, this flux into charge. So this flux is n C bar by 4, this C bar is V average, and you know the V average depends on the temperature, so it comes like this. And finally you get the current density related to the temperature number density like this. So you get the number density here from this equation itself as J by E square root of KT by twice ME, and T you got from above from the slope. So you are able to determine the electron number density inside the plasma. So this is a very simple technique and very reliable method of measurement for electron number density and electron temperature inside the cold plasma devices. Now we covered the thermal plasma technology areas. The first one we addressed is an environment friendly route for waste to wealth. Now here what we are showing is that it is a societal application. From huge dumping ground you can get a very neat, clean and green, healthy environment. So in this case this plasma can help. How it can help? This plasma is a very high temperature object. When you are talking about thermal plasma, this is the kind of plasma jet that comes out from the plasma torch. So this is the plasma torch that we have discussed in our class. The jet that is coming out, it may have a temperature beyond 8000 degree Kelvin in this zone. And you can see that nowadays the devices are available which can throw very huge jet, large volume plasma, and because the temperature is so high, so most of the materials, whatever may be the form, may be highly carcinogenic, they get broken into their constituent atoms, and sometimes they form ions as well because it is a very high temperature plasma. But anyway, they can break the bonds. For example, if you have say a bond of C and N, so that forms the cyanide. But when you break the bond, they becomes carbon and nitrogen. Both of them are benign. So this is basically the underlying principle for making the hazardous waste into benign waste. In Gazette of India, this is the only method which is listed as the method for treatment of plastic. Otherwise, when you burn the plastic at normal temperature, sometimes they generate very carcinogenic compounds like dioxin and furan. Some of the compounds, they have isomers which are carcinogenic at the level of nanograms. So you need to control the emission of these hazardous harmful molecules in the level of nanogram. So that is why plasma becomes very useful in mitigating this kind of waste. So this plasma can be used for one thing, that environment, clean and green environment. Then you can use for electricity. This is because when you are burning waste, they are having huge store of energy. For example, they are nothing but carbon, hydrogen, nitrogen chains. So when you burn them in the high temperature plasma, most of them result in exothermic reaction, and because of plasma you get very vigorous reactions. So that helps you to generate huge amount of energy from the waste itself, and that energy you can use to generate steam which can rotate turbine and which can produce electricity. It can produce steam because it is anyway generating energy, so that steam can be used in the chemical industries. Then if you are going for this gasification, sometimes it is very much possible to generate carbon monoxide and hydrogen out of this waste. That combination is called syngas, and if you are able to purify it, make it free from these carbon particulates, then this gas, combination of carbon monoxide and hydrogen, can be used exactly like compressed natural gas, CNG. So you can run the engines, you can drive the vehicles like that. Then you know that hydrogen is a future generation fuel. So if you are able to separate CO from this combination, then you can get hydrogen, and which is the next generation fuel. Otherwise also, if you are producing, say, the syngas not in very huge amount, then what you can do, you can use catalytic converter, which are readily available to convert this CO and H2 to methanol. And this methanol is a liquid which has very high import or export values. Okay, India is currently importing the methanol. See, these are in crores. So in different years, how much ethanol has been imported. So these are this other method of using this technology of thermal plasma, where you are using this plasma to mitigate the electronic waste. This many of the modern gadgets is having the leads which are having this very precious materials like silver, golds. They make the leads out of that because of good to provide good connectivity, electrical connectivity. Now when these gadgets are not working, so you just throw it out. So you can use plasma to extract the valuables from this electronic waste which has been dumped in the dumping ground. This kind of management we call urban mining. This is because we are getting very useful material like copper, iron, aluminium, and of course the precious metals. Where from we are getting? We are getting from the waste that is dumped in the urban area. So the mine is there in the city itself, and you can collect those the waste and you can get the material extracted from there. In most of the cases, the material is highly pure. So that makes the application of plasma for waste to wealth. Usually you use a primary chamber like this, where the torches are fitted at the bottom, the waste comes from the top, and in this zone because of the limited availability of oxygen, the gasification takes place and you get the carbon monoxide and hydrogen generated. So this is the gasification zone. Then this is the freeboard zone, and later on you can process the gas which has been generated. You can simply incinerate it, or you can use it to generate, as I told you, for methanol, for hydrogen production, for syngas production, for electricity generation, or only for steam. Okay, so these are different applications of thermal plasma in the waste processing sector. So typical process flow diagram for the waste mitigation is shown over here. These are the carcinogenic components which I was just talking. This most toxic isomers of dioxin and furans. So these are the thing. Not all of them are very toxic, but many of them are extremely toxic, as shown over here. Now they are basically having the benzene ring kind of structure, and somewhere chlorine is attached, somewhere oxygen is attached like this. Our purpose is to break the bond and make them benign, as I told you. Now the other thing is that because of the very high temperature here, the reaction, that is gasification, takes place in a very vigorous manner, and that results in very high efficiency gasification. So here what we are showing, that this is the MSW, and at the end what you are getting at the bottom of the reactor, nothing almost. So 9 kg, this is a controlled experiment, and you are getting 9 kg reduced to just 26 grams. Okay, so that is something very remarkable when you are going for this plasma gasification, and you see that whatever you are emitting, that is almost nothing. Your pollution is nearly zero. Now, these are some emission studies which have been done, and we are seeing here that all the emissions are within the limit prescribed by the Pollution Control Board. So, to summarize, superheated thermal plasma processes, easy availability of high temperature, this may be 600 to 800 Kelvin, but that is not the thing actually. High temperature is 6000 to 8000 degree Kelvin. Now, aggressive reaction via ionic and atomic species. So, high temperature what you are seeing here, it should be 10 less, it is here. So, it should be 6000 to 8000 degree Kelvin. Then aggressive reaction via ionic and nascent atomic species. Equal applicability to polar and non-polar materials. This is important because sometimes you are able to apply this techniques only to polar material. Like if you are using for microwave, you know that on dry substance it doesn't work. When it is wet by water, the polar molecule, then it works there. You might have experienced in your microwave. Now it is this plasma is having very high enthalpy content. It is simple, rugged and compact system design. Then extraction of energy from organic content through gasification, incineration and utilization of energy extracted in the process. Much faster startup and shutdown time, nearly 100% metal recovery, significantly high throughput, no requirement of post-processing of metal separation as they do not melt and form a mixed ingot. So, these are some of the advantage of thermal plasma processes in the waste management sectors, and this is what you are seeing here is the extraction of metals from the PCBs, the electronic waste. What I was telling that it is urban mining. So you are able to see that this is coming as a slag, the aluminium content in the PCBs. So you are getting almost pure aluminium getting molten and then coming out in the form of slag, and then what you are getting this copper extracted almost in pure form here from the PCBs. This copper strips remains there in the the resin matrix which is there over which you are putting your components. Then these are the connecting leads where I was saying that you may have precious material, and how we get after the treatment of this by the plasma, you get this kind of thing, and here you can apply one magnet to extract the iron components. They will be attracted and they will be collected like this. So these are collected using magnet, and inside the matrix where the electronic components are attached, there are this copper foils inside, and then these are the connecting layers which may have precious metals which you can extract using conventional techniques. So this is a very easy way to apply the plasma technology in the electronic waste management sector, and earlier I have explained how they can be applied in the case of municipal solid waste management. So these are some some expanded image of those collections. So this is copper, this is recovered iron, this is recovered ceramics, and these are the metal beads which may contain the precious material. So I take a little break and I will be coming back after the break, and after that we will discuss the material testing under extreme conditions in the fusion area, how our thermal plasma technology can help there. Okay, so we will meet you after a little break. Thank you.